Engagement Specialist for Test Oil. We're very pleased to be hosting this webinar titled Lubrication Fundamentals, Lubricating Oil Basics. Before we start the webinar, there are a few things I want to go over. First of all, let me check my audio. If you can hear me, I would like you to please raise your hand by clicking on the little hand icon in the toolbar on your GoToWebinar application. Can you please do so now? Thank you. I see several hands being raised. Thank you. Now, I see the other thing I wanted to let you do is to let you know that everybody will be on mute during the webinar. This is to ensure a high-quality recording. We are recording this webinar so I can share it with you later on today. If you have any questions, you can always submit them using the questions field in the toolbar on your GoToWebinar application. If we have time at the end of today's webinar, we will address your questions. If we do not have time, we will address questions via email. Let's get started. I know you're all ready to begin. As I mentioned, today's presenter is Dwan Ruffin. Dwan has more than 12 years of experience working with power plant equipment and various industrial machining tools, as well as with a variety of turbine engines, including Rolls-Royce, General Electric, and PSM. He has also been involved with researching various aspects of machine maintenance, including cycles, fluid mechanics, and machine design. Thank you for joining us today, Dwan. I'm going to pass the controls on to you now.
Our apologies for the technical difficulties. Again, I'm Dwan Ruffin. This is Lubricating Oil Basics, and we're just going to get started. Today we're going to be talking about pretty much everything about oil. This course is actually a prerequisite webinar for our other webinar we host, report interpretation. So if you're looking into understanding better for your reports, to see what kind of data you can get out of it, how to relate it to equipment actually on the floor, this will get you ready and understand a little bit more about the oil, so the report interpretation will make a little bit more sense to you. Alrighty. All right, first off, what is the function of a lubricant? These six things here are pretty much everything that your lubricant does. It lubricates, it cools, cleans, protects, seals, and transmits power. First function, lubricate. Now, if everybody understands the process of friction, you rub two surfaces together, eventually they start to heat up, and eventually these can also bond together. So to cut that friction down, to stop that bonding, to stop that wear, we use lubricant. Lubricant goes between the two surfaces to have a super slick barrier, so they don't actually touch. They just kind of hover around each other. And if you can see the little asperities on the right-hand side here, if you look under a microscope at two surfaces, especially metal, you'll see that the surfaces aren't perfectly flat. You have these asperities in here. It's almost like peaks and valleys. And when you put these two pieces together and rub them, it's almost like putting two saw teeth together. So to combat that, the oil actually forms a film and fills these gaps up, so this surface is totally smooth. And this is how we actually reduce friction through lubrication. Another function of your lubricant is to cool. When these surfaces start to rub together, or if you get heat transfer from other components in the machine, that heat goes through the metal to other areas. And a lot of times this heat can be extensive and it can start to deform your metal. So to also aid in keeping down that heat, your lubricant forms as a coolant. That actual lubricant can carry that heat and that energy away from your oil to another area, and usually to a reservoir or a cooling unit where it disperses that heat and keeps the temperature of the metal down. Another function is to clean. Just as heat is carried away from your machines, dirt and particles are also carried away. In particular, if you have like a machining process, you get the metal chips in there while you're actually drilling or milling. And if you keep those in the oil, they can go back in, and as you're grinding or as you're milling, they can start to put other scratches in the surface or start to dig in and gouge. So to cut that down, the lubricant actually flushes and carries away those particles so you don't get that back in your process. Lubricant also is a protectant. When you're storing metal equipment or any kind of metal parts, you usually coat it with some kind of oil or some kind of barrier to keep the outside elements off from corrosion or water or process contaminants, anything like that. So that's how your oil actually is served as a protectant. It also provides seal capabilities. In particular, this slide here shows grease packing. And the grease is a good way to keep particles out between, say, a seal and the outside elements. You can pack it with grease, or sometimes you got oil layers in there that can actually keep the particles and the dirt and stuff out. Your lubricant also transmits power. Here we have a hydraulic unit. Oil fills up this reservoir here, and it acts as a power transfer, or it multiplies the actual force in there. And you can use that. You may have a small amount of force going in, which would be your pump. Once you pump that fluid into that cylinder, that is multiplied by your diameter of your piston around here. And that builds up a more powerful force than you actually pump. Your actual pump is actually pumping. So it actually transmits that power into to do work. All right, and we're going to get into the lubricant types. Two basic lubricant types. You have mineral oils and synthetic oils. Now, mineral oil comes from the ground. We mostly know it as crude oil. You pull the crude oil up, you process it, and end product, one of the end products that you get is mineral oil. Synthetic fluids are man-made. These have molecules that have an identified structure, and the properties are pretty predictable. Synthetic fluids are usually engineered for a specific purpose. May it be keeping the heat down from high heat situations, or if you need an extended friction modifier, or if you need to cut down friction in extreme areas with high heat or high pressures. The synthetic oil usually does a little bit better job than the mineral oil in certain instances. Sometimes mineral oil can be a little better, but there's a lot of controversy between those two. Now, your API base oil categories. First base category you have here is a group 1. Be right in this area. And this gives you the amount of sulfur content in that particular oil, amount of saturates. This is less than 90. One big thing here I want you to take away from this slide is your viscosity index. If you don't know what a viscosity index is, it's kind of a good way to tell if you have how your oil handles heat extremes. For instance, if you live in Alaska or the North Pole or something, you're negative 20, 30 degrees at times. Say that same equipment may see temperatures when it's ran up to above 130. An oil's ability to maintain a consistent viscosity and not vary too much from those two temperature extremes is your viscosity index. The lower the number, the lower your index, or the less capable your oil is to remain stable in in between those extremes. Now, your group 2 oils, it's got less sulfur in it, higher saturates, and your viscosity index is about the same as the group 1 oil. Oh, and I'm sorry, I missed this part here. The way it's manufactured. Solvent refining will be a basic way to refine the oil. Hydrocracking, a little bit more detail, a little bit better. You get a little bit better end product out of it. Now you get to your group 3 oils here. Your group 3 oils just have less than or equal to 0.03 sulfur, greater than 90 or equal to for saturate percent. Your viscosity index is over 120. Really, really good oil for handling heat extremes. You cool it down to negative 30, and then you go up to 130 degrees. The oil doesn't vary too much because of that high index. It can really handle and stay stable during those conditions. Manufactured, this is hydrocracking, and also iso dewaxing is used. So these will be, if you ever hear anybody talk about these oils have been highly refined. Well, right here shows kind of down a list how you go higher and higher as you go through the refining process. It would be similar to, say, a vodka. You got the lower vodkas that aren't really distilled that well or a different process. And the higher grade stuff is triple distilled or it's been processed a little bit higher, it's been refined better. Same thing goes with oils. And you come down here to your group 5s or group 4s and your group 5s. These will be like your synthetics. You got your PAOs, synthetic hydrocarbons, and you also have your group 5 oils, esters, the silicons, and the PAG oils. And these will be your most expensive oils, your highest engineered oils for extreme conditions and particular conditions. Now, mineral oil versus synthetic oil. To give you a good idea how the end product comes out, mineral oils, you see the old experiment. If you take, say, a flat piece of wood or a door, you fill a room full of, say, different kind of balls, tennis balls, beach balls, basketballs, baseballs, all these different kinds. And you lay the door on top of those balls. Now, if you stand on it, it's kind of uneven. Some areas, some balls may be stressed higher. The bigger ones get the most stress. The smaller ones may not even get untouched. Now, this also puts more wear and more pressure on different spots on the door. So the surface is actually uneven, and in our case, this will be uneven wear. You'll get more wear in one area, and that starts a progression of wear that can tear down your metal surfaces after a while. Now, with synthetic oils, this will be equal to, say, filling that room up with everything the same size, all tennis balls or all beach balls or all basketballs. The door will fit nice and flush on these balls. It will run nice and smooth. Every surface is equally loaded. That's pretty much how your synthetic works when you're looking at in your machines. And when these synthetics are engineered, the molecules are engineered just for that reason, to have everything uniform and identical. Mineral oil refining process. If you never knew how mineral oils were made, you start here, you pull the crude oil out the ground, you start to heat it up, and at different temperatures, you start to release different products. Lowest temperature here is 20 C, you start to get gas. You get naphtha gas, and just around here at about 90 to 100 degrees Celsius, you start to get gasoline. You keep heating that stuff up, you start to get kerosene. Right in here you get gas oil, and diesel. And then the heavier stuff down at the bottom, you start to heat up a little bit more. Around 300 C, 280 C, you start to get your lubricating oil, right here where we're at. If you keep heating that up, you start to get the residual stuff. This will be stuff you use for tar and asphalt and things like that. But right now here, we're looking at the lubricating oil, right around 300 C. Synthetic oil. The advantages: extended range of service temperatures, resistance to oxidation, extended service life, you have a cleaner running system, energy savings due to lower internal friction. And again, as I mentioned, with the analogy of all the equal molecules or equal size balls that you would have. This reduces your friction, makes a nice smooth surface. The smoother the surface, the less friction you have, less energy you use, the less heat you generate. Disadvantages. The cost of synthetics is pretty high, just due to the extra engineering and extra processing that they have to do. Sometimes you can have compatibility issues. When you start to use esters and silicons, you can have issues with paint, seals, different packings, and other fluids coming in contact. It can react with it, or you can shrink seals or disintegrate seals. So you always got to keep that in mind when you're switching to a highly refined or highly engineered synthetic oil. Higher disposal costs. Film strength consideration for gear applications. Not so much now, but sometimes you can run into this. I think it applies more to older equipment that you may have some issues with using oil, some synthetics in some applications. But for the most part, synthetics now, you can pretty much use in a wide range of equipment. Now the additives. These are chemical compounds added to get specific properties. And we'll get into the additives and what kind of properties they will give you in a little bit. These are added to improve performance characteristics. These are formulated to provide specific set of performance parameters. And these also can have detrimental side effects. Now, for lubricating oils, your basic makeup. Your engine oils are the most highly additized oils there are. This being because of the internal combustion process. You've got acids, you've got outside elements, you've got fuel, you've got fire. You get different deposits from this internal detonation of air and fuels. So to combat that, these oils are highly additized, be it cleaners, additives to reduce smog, things such as that. Now your gear oils, your AW, hydraulic fluids, and your transmission fluids, still highly additized. They can be dirty environments. You need cleaners. You also need some cushioning for gears being together. So you got a lot of additives in there. Not so much as the engine oils, just because the systems are usually sealed. Now, your turbine oils, your R&O hydraulic oils, and your compressor oils, you don't need a lot of phosphorus, which is used for extreme pressure issues or extreme pressure environments. You don't need that. You don't really need as many cleaners because these environments don't really get dirty. So it's only a small amount of additives that you will find in, say, turbine oils and these R&O hydraulics. Common additives, you have extreme pressure additives, oxidation inhibitors, detergents, rust inhibitors, foam inhibitors, and pour point depressants. And depending on what kind of machine and what kind of applications it is, you choose an oil by what kind of additives is in it. Some oils, they don't need the extreme pressure additives, so you don't find that in, say, a turbine oil. You don't find detergents in oils where they have systems that are pretty clean. Rust inhibitors, anything that's subject to the outside environment or any kind of acids or process contaminants that may deteriorate the oil. The rust inhibitors, you will find a lot of that in those type of oils. Typical oil packet, additive packages, start here up at the top with the EP, gear additives. The EP just stands for extreme pressure. So if you got a heavily loaded gearbox, that's extreme pressure. So that's one thing why you use a gear oil. Now gear oils, they don't have magnesium, calcium, or zinc. These are used for cleaners and also anti-corrosion. The main thing in those you'll find is phosphorus. And the phosphorus is to pretty much cushion the banging of the gears or the loaded gears together. What that EP additive actually does, it almost foams. If you have a no oil situation, the actual additive can extend the life of those gears without oil. You get like it actually reacts with the metal and forms a super slick surface to give you a little bit added protection when those gears come in contact if you end up having no oil. AW hydraulic oil. These have calcium in it for cleaning, and these telltale sign of an AW or a hydraulic oil, the AW just means anti-wear, is the zinc and phosphorus. Same thing, you have some wear going on in there, and you also need the zinc in there to also combat that. Turbine oil. Turbine oil pretty much doesn't have anything in it. You'll find some antioxidants in there for outside water coming in or condensation or getting into the system, but that's about it. You don't really have any heavy loads in there. You don't have any internal combustion coming in contact with the oil, so it's a fairly clean and basic oil. Compressor oil, pretty much the same thing, goes along with the turbine oil. You have PCMO for gas. This will be a gas engine. You have, and remember, these are the most heavily additized oils, will be your internal combustion, be it gas or diesel. You have magnesium. And some of these elements or some of these additives come in different flavors. They come in different amounts. It really depends on the manufacturer. You know, what kind of product are they trying to make, or what different additives do they believe works the best. That's where you start to get in all the stipulation of different brands and stuff like that. But in the gas engine, you have magnesium, you have calcium, high levels of zinc, and phosphorus. In the diesel engines, you typically don't see magnesium in there. You have a lot of calcium because of the added dirt and soot that's actually into the oil, so you have to have a little bit more cleaning additives in there. And as well, you have the zinc and the phosphorus. And all of this stuff is in parts per million. And you would see this on your reports. So when you get your report and you'll see I have a gearbox, and you look at the data to see actually what additives are showing up in this actual gearbox on your report. Well, if you see, say, zinc and phosphorus, and you have, say, a 620 gear oil, it's more than likely mixed with something or something special, because you should just pretty much have a high level of phosphorus in it. A couple other things here and there, but you kind of get the idea. You really shouldn't see magnesium or high levels of calcium in your gear oil. So right off the bat, that has some value when you're actually looking at your reports to see if, hey, is somebody topping this off with, say, motor oil, or are they putting the right oil in it? That'll kind of aid in finding out what you got. One of the most important properties, if not the most important, is your viscosity. This is defined as a fluid's resistance to flow. Most important characteristic of oil, and has a direct correlation to temperature. And that again goes with the viscosity index that we talked about. Having a higher viscosity index means your actual viscosity deviates less between extreme temperatures. Kinematic viscosity, this is more standard viscosity. Most of the time you see results reported in kinematic, or done in kinematic viscosity, which is written in centisols, or CFT. This is measured at 40 degrees and 100 degrees Celsius. Seaboat viscosity, not used as much, but definitely still around. This is reported in Seaboat Universal Seconds, or SUS. These lubricants, when you do this test, are measured at 100 and 210 degrees Fahrenheit. So it's a little bit different in kinematic viscosity. Basic ISO grades for your lubricants. These start off at an ISO VG of 2, typical, all the way up to 3200. Now these will be your readings at different temperatures, your kinematic viscosity. This will be at 40 degrees C. And then you have your maximums over here, your mins and your maxes. So if you're getting a report and you're looking to see if your oil viscosity is within standard. Industry standard is plus or minus 10%. We'll give you like a marginal. Plus or minus 20% exceeding that will be a critical. So in here, your range for ISO of 2 will be 1.8 to 2.42. And the farther you fall outside of that range is when you start to say, is it 10% or 20% beyond, where it should be. And that's kind of how you judge it. All the way down here to something standard like a 32. Typical bearing oil or turbine oil, 29.8 to 35.2 is the range. When you start to fall out of there, then you know you're either too low or too high. And just to give you a little heads up, when you get your reports, if you haven't looked at them yet, if you see something starting to fall outside of the realm of what the viscosity should be, you can always revert back to the additive package on your report and find out, hey, does this match the additive package that should be found in this particular oil? If that doesn't match and your viscosity doesn't match, it kind of tells you, hey, you got a different oil in here. That's why this course is pretty much a prerequisite, just to get you prepped up so when we do go through report interpretation, everything starts to make sense to you. You can kind of do your own detective work to find out, hey, what's going on with this oil. SAE oil weights. Sometimes these get confusing. You get a lot of people asking, what does the W mean, and should I use a 20 weight in my car, should I use a 40 weight or a 50 weight? Well, basically, the higher the weight, the thicker the oil. 50 weight here on the end would be something used in a very heavy-duty vehicle, construction equipment, race applications, stuff like that. 20 weight will be tight clearances. Most of your modern vehicles are switching over to 20 weight. Some are even lower than that right now. They use it to heighten efficiency and cut some costs down. Now, they kind of explain the multi-grade nomenclature we have here. The W pretty much stands for your winter weight. So this first number here right in front of the W is the weight in the winter. And almost it sounds backwards. You would think in the cold, the oil actually, gets thicker. But the engineering of it and the modifiers that are put into these oils, it actually emulates that of a 10 weight in the wintertime, below 32 degrees. Now, above 32 degrees will be your summer or spring weight. The actual oil, when it's heated, it actually emulates a 30 weight. So it gives you a little bit more cushion, a little bit more protection during the hot weather or hot conditions. So if you say, hey, I need a 30 weight, it's a multi-weight oil. This is kind of what they mean. below 32 degrees, the oil changes its chemistry or changes its structure to actually allow flow during these really cold temperatures. You don't want to have honey in your sump at negative 20 degrees. You need something that's still going to stay pumpable when it's cold outside. So you want to get an oil, say, these are usually, say, a 5W30 or 10W30. A 5 being a little bit easier to pump during cold weather than a 10. It'll be a little bit thicker during the cold weather. And it depends on the application, and what the manufacturer actually specifies that you should be using. Proper viscosity. Factors that affect proper choice of viscosity. So if you're choosing what viscosity to use in a machine, and you may not have a recommendation from a manufacturer, or you think the recommendation is not good for your actual application, or maybe custom work, a good thing to take in consideration when choosing viscosity is a few things here. For low viscosity oils, they provide good cooling. Poor load handling, just because it's not as thick, you have a real thin film, so you got to keep that in mind. And low internal friction. So you can really speed, usually your lower viscosities are for high-speed applications, things that aren't loaded, very heavily loaded, and also when you need some good cooling. Now your high viscosities are for slower moving equipment with heavier loads. You don't have as good a cooling as you do with the low viscosities. Good load handling ability, just because of the film is a little bit thicker, a little bit more cushion available, and higher internal friction. It always takes more friction to move something that's a little bit thicker and a little bit slower. It takes more energy to move it around. So if you're choosing an oil for especially like a custom application, you want to get somewhere in between here to kind of figure out, between high and low viscosity. Just to give you an idea of the, say, a turbine engine will be a 32 viscosity. High speed, low load, can generate a lot of heat. High viscosity would be a gear oil. Large, slow-moving gears, a lot of contact, a lot of load. So you can use that as a basic rule of thumb. And actually, here is your basic rule of thumb. Your load, higher the load, the heavier the oil. The lighter the load, the lighter the oil. Temperature. The lower the temperature, the thinner the oil. The higher the temperature, the thicker the oil. Speed. The faster the speed, the lighter the oil. The slower the speed, heavier the oil. That concludes our webinar for today. You can forward any questions to my email or send them to Test Oil, or just get in contact with Megan. I want to thank everybody for joining us today, and I'll turn it back over to Megan.
Thank you all for attending today's webinar. In just a few hours, you will receive an email with the survey and a link to the recording of the webinar. Thank you again, and have a great day.